So this video is more about quantifying the amount of energy to do certain things to a substance. For example, the heat of fusion, which is A, is the energy that would be required to melt a gram of a substance. And the energy is measured in something called joules. That's Joules, but I'll just put a J next to something, and you should know that means a certain amount of energy. The heat of vaporization is the amount of energy to boil 1 gram of a substance. And the specific heat capacity is the amount of energy to change 1 gram by 1 degree Celsius. So if you had, let's say, a gram of water, how much energy would you have to add to raise its temperature by 1 degree? Now, I've changed the heating curve and added a little bit of information to help us quantify things. What I've said is we have a 10-gram sample, okay, and that we're heating at a rate of 100 joules per minute. So knowing how much mass we have and the rate at which we're heating, we can figure out how much energy it will take, let's say, to melt our 10 grams. Watch, let's do that first. Let's do the heat of fusion. So the substance starts melting at point B and finishes melting at point C, which means it basically takes 3 minutes for it to melt. So this is 3 minutes total. Now notice, I'm not starting at time 0 here. I'm starting at the time it starts to melt to the time it ends melting. It's completely melted or fused, right? So what that means, since it takes 100 joules per minute, right, so we can take our 3 minutes, and we can go, well, it's 100 joules per 1 minute, and that basically says it took 300 joules to melt our sample. But we want the amount to melt a single gram. Well, it took 300 joules to melt 10 grams. Now we can set up a ratio, or we can just divide through, because essentially you can do, well, 300 joules per 10 grams is X joules per 1 gram, right? Set up a ratio like that. But really what you're doing is just dividing the 300 by 10. So what you find is the heat of fusion for this substance is 30 joules per gram. Let's do the heat of vaporization over here. Now, to boil the substance, well, it started boiling at minute 10 and finished at minute 14. So it took 4 minutes to boil. So instead of 300 joules, it took 400 joules to boil our 10 grams. Which means the heat of vaporization is going to be equal to 40 joules per 1 gram. I just divide the 400 by 10 in that game. Or I could just do this, cross out zeros. That works too. Because when you're dividing something by 10, you just move the decimal one place over. Specific heat capacity is a little more complicated. And I'm actually going to erase some of the math down below here, okay, so we can do it in the space over here. Now the specific heat capacity is so specific that it's different for different phases of matter. And because it involves a change in energy, we don't use this for a phase change. Phase changes have no change in temperature, so there'll be no going up by a degree Celsius. So what we can do is look at, let's say, the liquid. Now, we always get these straight lines with a constant slope. So here's our liquid, and we could ask, what is the specific heat capacity of our liquid? Well, in the 5 minutes that it was liquid, because it starts as a liquid at minute 5, ends a liquid at 10, it took 5 minutes. So in those 5 minutes, right, we had a total of 500 joules of heat energy. And it took 500 joules to raise the temperature of 1 gram. Now watch, I'm going to put it underneath, of 10 grams, sorry, not 1 gram. And changed it by, let's see how much the temperature changes. It's 50 to 110, change it by 60 degrees Celsius. Now I'm going to pause for a second. Now when I actually do the math there, nothing cancels out, so I actually did 500 divided by 10 divided by 60, and that gave me 0.833 joules per gram per degree Celsius. This means if I add 0.833 joules to 1 gram of the sample, it will go up by 1 degree Celsius. Now I can do this, so this is the specific heat capacity of the liquid, for this is just for the liquid. I could do it for a different phase of matter, and what you want to notice is there's something different here. If you look at the gas, the curve is much steeper, as is the curve for the solid. Let's do the gas one, okay? So for the gas one, right? Let's see, for 2 minutes. Right, which is 200 joules. Hopefully you understand, 100 joules per minute. So it took, in just 2 minutes, we added 200 joules of heat to our 10 gram sample. And how much did the temperature change by? Let's see. It starts at 110 and ends up at 100. I'm trying to see this in my 180. No, 170. So from 110 to 170. So it changed by 60 degrees Celsius. Now what you want to notice here is that you add much less heat, and it changed by the exact same amount of degrees. So if I do the math on this one, and I'm going to break up my calculator, I do 200 divide by 10, which just gives me 20, by the way, and divide by 60, I get a much smaller number, a 0.333 joules per gram per degree Celsius. And what this means is it takes a lot more heat energy to change the temperature of the liquid than the gas. And you'll find that things that have low specific heat capacities, they get hotter much faster. So if you were like to compare water to, let's say, a piece of metal or the pavement, right? The reason why the pavement at the beach gets so hot, or the metal on your car gets so hot, is because metals in the pavement have low specific heat capacities. It doesn't take a lot of energy to change their temperature by a lot and to get really, really hot. So finally, I think I'm going to let you try to figure out the specific heat capacity of the solid phase. And I'm going to tell you to try to do that on your own, and then I'm going to give you the answer without writing out all the work. So since the temperature changed by 40, and it's still 10 grams, and it took 2 minutes for the solid to raise its temperature from 10 up to 50, your final answer will be 0.5 joules per gram per degree Celsius. By the way, in this video I did not bother with significant figures because I wanted to get the concepts out.